Hello Year 11. I'm sorry I can't be with you today, but unfortunately I'm having to self-isolate. There should be a cover teacher with you who will take you through this video lesson and provide you with resources and so on. So to start off with, let's have a little recap of what are the names for, the rules for naming alkanes, how many bonds can carbon form, what is the general formula for an alkane. Just remind yourself of the key points above by looking back through your exercise book, and we'll go through the answers shortly. Please pause the video to do that. Okay, names for alkanes. You recall that last time we talked about monkeys eat peeled bananas. If something's got one carbon atom, it's meth. If it's got two carbon atoms, it's eth. If it's got three carbon atoms, it's prop. If it's got four carbon atoms, it's bute. Monkeys eat peeled bananas. After four carbon atoms, it's just like shapes. So 5 carbon atoms, it's pent. 6 carbon atoms, it's hex. 7, it's hept. 8, it's oct. 9, it's non. 10, it's dec, and so on. So the rules for naming alkanes are: the prefix is monkeys eat peeled bananas, meth, eth, prop, bute, and then after that it's just like shapes. The suffix, which means the ending, ends in anes for alkanes. How many bonds can carbon form? Well, it's in group 4, so it can form 4 bonds, and that's going to be really important today when we come on to drawing the display formula of hydrocarbons. And the general formula for an alkane that we covered last time, where N is the number of carbon atoms, is CnH2n plus 2. Okay, although normal chemical formula, such as C5H12, remember this is CnH2n plus 2, so 5 times by 2 is 10, add on 2 is 12. Although this is a way that we use to describe alkanes, this is called the molecular formula. It doesn't really convey which atom is joined to which other atom. So to get around this, we use something called the displayed formula, which displays all of the bonds, hence the name displayed formula. It shows which 4 other atoms each carbon is bonded to, but even these don't show the actual 3-dimensional shape. For that, we use models such as this, which is sometimes referred to as a ball and stick model, because the atoms are represented by spheres or balls and the bonds are represented by sticks. In terms of alkanes then, this is methane, ethane and propane. You can see here what we've already talked about, that each carbon forms 4 bonds. So methane is the molecular formula is CH4. Here it is shown in terms of that ball and stick model. Ethane is C2H6. You've got 2 carbon atoms. 2 times by 2 is 4. Add on 2 makes 6. Propane and so on. Here's butane, C4H10. This is the displayed formula. This is what it looks like in terms of its model, in terms of the ball and stick model. Pentane, C5H12. Again, here is another model of pentane. So we didn't quite get round to this last lesson, guys. Can you copy and complete this table? So for methane, you want to draw out its molecular formula as well as its displayed formula. This probably will take up at least a page in your exercise books. Pause the video, and when you're ready, we will resume with the answers. So the answers are as follows. Methane is CH4, ethane C2H6, propane C3H8, butane C4H10, pentane C5H12, hexane C6H14, heptane C7H16 and octane C8H18. Tick them off. If you didn't have them, you can add them in. In terms of the displayed formula, I've only shown 3 because I can't really fit many more on the slide here. But methane is CH4, so it's a carbon with 4 bonds to other hydrogens. For butane here, you've got 4 carbon atoms in a chain, but each carbon can form 4 bonds. So on this side, you've got 3 hydrogens, 1, 2, 3. And then the same is true on the other side. And in the middle here, you've got a carbon bonded to 2 others, which means that 2 bonds are already used up. So the other 2 go to hydrogens. And exactly the same is true for octane. So I've shown you 3. Hopefully you've managed to fill in the others as well. If you need to pause the video just to check these off, please do. Okay, back to crude oil then. You'll remember that crude oil is a mixture of different hydrocarbons. What I'd like you to do is to pause the video in a moment and think about your daily routine, from when you wake up in the morning to when you get to school, and all the way through to travelling home and having dinner at home and so on. I'd like you to list all the occasions when you use a fraction that is something to do with crude oil, be that petrol, diesel, paraffin, anything you can think of. Just pause the video, have a brief discussion for a minute or two, and then we can resume the video and I'll go through a few answers, a few thoughts. Okay, so you wake up in the morning. One of the first things you'll do is go and use the bathroom, and while you're there you may brush your teeth. Even if you don't brush your teeth straight away, if you have some breakfast first, we'll come on to breakfast in a minute. But the tube that houses the toothpaste is made out of a polymer, which itself is manufactured from crude oil. And even the toothpaste itself, there will be lots of ingredients within the toothpaste which uses crude oil in its manufacture. Let's say you pop downstairs and you have some breakfast. Maybe you have your breakfast first and brush your teeth later. But if you think about let's say you have cereal for breakfast, the cereal box itself is made out of a polymer. Well, it's made out of cardboard, but the ink and so on and the plastic coating around the cardboard will be made out of crude oil, as will the ink. Inside the cereal packet, there is a polythene bag containing the cereal. That itself is made out of crude oil, the bag. And that's not even going so far as to talk about the fact that the cereal was manufactured in a factory, probably using crude oil or other fossil fuels to make the cereal, or manufacture it from wheat and oats and what goodness knows what else. And then it has to be transported to the supermarket via some sort of truck or lorry. Again, that's crude oil, such as diesel or petrol. You then drive to the supermarket, you put the cereal into your shopping trolley. Oh, there's lights inside the supermarket and heating. All of that uses crude oil. And then you drive home again. So even without even thinking past breakfast, you've used loads of crude oil before you've even left the house, whether you walk to school or get the bus. Oh, there's crude oil being burnt there again in the form of diesel or petrol. And that's even before you've even gotten to school. So crude oil is used all throughout our daily lives. The thing about crude oil though is that crude oil as a mixture isn't terribly useful. We need to separate out the various different alkanes within the crude oil using a technique called fractional distillation. And fractional distillation we looked at the start of year 10 when we looked at separating mixtures. This is effectively a revision. However, we're going to look at this in a bit more detail in terms of just separating out the fractions, the useful portions in crude oil. So we're going to show you a video. It's quite an old video, but it's a good one nonetheless. What I'd like you to do is to make notes during the video. What do you think are the 5 key points from the video? The video is on the next slide, guys. Hopefully you're ready and listening attentively. Here we go.
Crude oil is a thick, dark brown liquid found deep in the Earth's crust. It's a mixture of different hydrocarbons. molecules made of hydrogen and carbon. Some molecules in the mixture are very small, just a few atoms joined together. Others are far more complex, with many atoms forming long-chain molecules. But as a mixture, it's useless. The different hydrocarbons need separating. The technique used is distillation. This simple apparatus is set up in a fume cupboard. Mineral wool stops the mixture spitting when it's heated. Crude oil is dropped into the bottom of the tube. A collecting bottle is put in place. And a thermometer level with the sidearm monitors temperature. The final step is to gently heat the mixture by immersing the tube in a hot water bath. The hydrocarbons with lower boiling points begin to vaporise immediately. They're flammable, so it's safer not to heat with a naked flame. As the vapour rises, it enters the sidearm, where it cools and condenses. This happens at about 40 Celsius. The hydrocarbons which boil at this temperature drip down the sidearm and form our first fraction. It's a colourless liquid. The temperature stays at around 40 until all the hydrocarbons with this boiling point have vaporised. The hydrocarbons left behind aren't hot enough to vaporise. Their boiling points must be higher. Once the first fraction has been collected, it's safe to start heating with a Bunsen. As the temperature rises, other hydrocarbons begin to boil. A new fraction is collected at about 60 Celsius. It's slightly yellow in colour. And so the process continues. By carefully heating the oil and collecting the liquids which condense at a number of different temperatures, the many different hydrocarbons in crude oil can be separated. This is known as fractional distillation. On a larger scale, a fractionating column is used. The oil is heated with an electric heater for safety. The vapour is condensed by a Liebig condenser and is collected in a conical flask. Hot vapour rises up the fractionating column. It's a long way to go, and the further from the heat source, the cooler it gets. Most of the vapour condenses on the glass spiral inside the column and drips back into the mixture. Only the hydrocarbons, which are still vapours at the very top of the column, enter the sidearm and condense to liquid. Industry uses the same process, but on a mammoth scale, in huge fractional distillation columns. The hot oil enters near the bottom, at a temperature of 330 degrees Celsius. The column becomes cooler towards the top. Fractions which remain as vapour at 85 degrees Celsius go straight to the top and are piped away. Different hydrocarbons condense at different temperatures, running off at various levels. Those with lower boiling points are collected at the top. Those with higher boiling points run off nearer the bottom. The longer the molecules, the higher the boiling point.
Industrial distillation separates crude oil into useful fractions, each containing molecules of a similar size.
Okay, so as part of the video, you saw this, hopefully. And what does it mean? Have a little chat, because it's important, and we're going to think about the crude oil in the context of fractional distillation. Okay, now that you've had a chat about that diagram and what that diagram may mean, the cover teacher should have handed you, or maybe they're in the process of handing out to you, this worksheet. I'd like you to work through the worksheet, guys, at your own pace, hopefully at a reasonable pace. I think that the whole worksheet shouldn't take you any longer than about 15 to 20 minutes. And then we'll go through the answers in turn for each part of the worksheet. Here are the answers then, guys. Here's the answer to the first part. Well, crude oil is a mixture of different hydrocarbon compounds, and hydrocarbons are substances which contain hydrogen and carbon only. We can separate out the different compounds in crude oil using a technique called fractional distillation. The different components, those that we call them fractions generally, within the oil will boil or evaporate at different temperatures. The compounds which come off at different temperatures are known as fractions. If you need to pause the video just to make sure that you've got those answers, as ever, can you tick them off if you've got them right? Can you write them in if you haven't? In terms of the diagram of the experiment, in the video that showed a fractionating column, you don't have to use a fractionating column for fractional distillation, but it helps because it's got a fractionating column in it with a temperature gradient, so it's hot at the top and cold at the bottom. Hot at the bottom and cold at the top. However, this is the experimental setup that you'll often see in a laboratory. It's technically simple distillation, but if you do it slowly, it can be used as fractional distillation. You've got a round bottom flask here at the bottom, although you might have simply written flask, that's fine. You've got a thermometer here, a condenser, and you can collect the distillate, or you might have written fraction here. In any case, that's absolutely fine. When you heat this up, it will boil, the vapor will rise and hit the thermometer so you can see the temperature at which that fraction is boiling. And when you start to see droplets coming down here in the condenser where the vapor condenses, you can collect those in the distillate here, making a note of the temperature here because that tells you the boiling point range of the fraction you're collecting. What's the trend in the boiling points of each fraction then? Well, the boiling point increases with increasing chain length, or you could say with each successive fraction. Either way is fine. What happens to the appearance of each successive fraction? Well, each successive fraction gets darker in colour. It starts off as being colourless, it becomes yellow, orange, brown, and eventually what you're left with over is a black residue. If you need to pause the video now, just pop your hand up so the cover teacher knows and tick off the answers or write them in if you don't have them. The next two questions then, the ease of lighting. Well, as the boiling point increases, as the fraction and the number of fractions increases, it becomes harder to ignite that particular fraction. What do you think happens to the quickness of burning and smokiness of the flame? Well, the quickness of burning decreases. In other words, it takes more time to burn, and the smokiness of the flame increases. It becomes more and more smokier as you increase the boiling point as the later and later the fraction. So hopefully what you can see is that the more useful fractions for combustion, for burning, as we will see, are the smaller fractions, the ones that have lower boiling points. And we'll go through the last little diagram next. Again, feel free to pause the video if you need to make a note of these answers. Okay. The next little part was how does the experiment work in the context of the diagram that we just saw? Well, fractional distillation separates the mixture of hydrocarbons in crude oil by their boiling point. The crude oil is first heated and evaporates or boils. The vapor rises up the thermometer where the temperature can be measured. That's the temperature, by the way, of the vapor. The vapor condenses in the condenser and the fraction drips down into the beaker where it is collected. This is a required practical, guys, so you need to know this practical inside and out. You could be asked for a method or to describe how it works. The bullet points that I've got on screen are one possible answer. You could have a different answer, but as long as it's similar to the one on the screen, that's absolutely fine. Again, if you need to pause to make a note of that, please do. Okay, the last thing on the sheet is this fractionating tower, which is how fractional distillation is done in industry. This is a huge tower. The crude oil is pumped in and it's heated, much like we've seen. It's hot at the bottom, it's cold at the top. So there is a temperature gradient here. There are small molecules at the top, large molecules at the bottom. You've got refinery gas that comes off at the top, that's bottled gas. You've then got petrol, which is used for vehicles, naphtha, which is used to make chemicals, kerosene, which is used for jet fuel, diesel, which is used in lorries for diesel fuels, lubricating oil, which is used to lubricate parts, let's say in a car or on a bicycle, anything with moving parts to make them move past each other easily, fuel oil, which is used in ships, factories and central heating, and finally you've got bitumen, which is used for roads and roofing. If you need to pause the video to go through those answers, please do. Okay, have a look at this diagram, guys. What does this mean? You should have seen this before earlier in your scientific career here at school, probably in year 8. My hint is what's needed for a fuel to burn. Pause the video, I'll give you a minute or so, and then we'll resume with the answers. So this is the fire triangle, guys. If you take any one thing away, the fire will go out. So hopefully what you said is the 3 things that are needed for a fire is heat, fuel, and oxygen. If you take any one of those away, if you take the heat away, if you take the fuel away, if you take the oxygen away, the fire will go out. When you spray water, for example, on a fire, you take away both the heat and you take away the oxygen. So the fire goes out. It's a way of combating the fire in 2 possible ways. Again, you will have seen that if you take a candle and put a glass over the top of it, you're removing the oxygen, so the fire goes out. If all of the fuel has been exhausted, like let's say, for instance, there is a forest fire or a fire in a campfire. Once you've used up all the wood in the campfire, then the fire goes out. Okay, can we write down a new heading, a new title really, which is combustion? Combustion is the scientific word for burning something, and alkanes are incredibly useful as fuels. That's their main use. Hence why when we talk about fossil fuels, we're talking about crude oil, coal and gas. Gas and crude oil, obviously we've seen how they are gotten at by drilling down in oil rigs and then separating out the various different fractions using fractional distillation. Here's a little setup though to see what happens when you burn a fuel such as natural gas. So this is a cross section. Here is a filter funnel. Can we be drawing this diagram out, guys, with a nice sharp pencil and a ruler? And this funnel is connected here to a U-tube. It's called a U-tube because it's shaped like the letter U. Inside that U-tube is some blue cobalt chloride paper, and that U-tube itself is immersed in an ice bath. Then that U-tube is connected up to a boiling tube which contains some lime water, and the whole thing is connected to a water pump, so that the gases from this fuel here, from the products of this combustion here, are drawn through this whole system here out through to the water pump. So there's 2 questions here. What happens to the lime water and which gas is given off? What happens in the U-tube and which substance is present? So first things first, hopefully what you'll recognise is that the lime water here it's a dead giveaway. When the lime water goes cloudy, you know that carbon dioxide gas has been present. two things happen in this U-tube here. The first is that it's cold, so inside here you'll note that there will be some condensation, right? The second thing that you'll notice happening is that the blue cobalt chloride paper goes pink. That indicates that that what has been formed in this U-tube is water. So there's two products of combustion here. The first is carbon dioxide. You know it's carbon dioxide because the lime water goes cloudy. The other product of combustion must be water because you see condensation on the inside of this U-tube together with the blue cobalt chloride paper going pink. Please pause the video, make sure that you have got this diagram copied out nice and neatly into your books with the heading The Products of Complete Combustion, and if you've listened carefully you should be able to answer these two questions. In any case, I'm going to go through the answers shortly. Pause the video once you've completed the diagram, we'll go through the answers. So inside the U-tube, you should see that condensation collects and the blue cobalt chloride paper turns pink. Both of these things tell you that water vapour is present as a product of combustion. Pause the video if you need to and add to your notes. Inside the boiling tube then, the lime water goes cloudy. You could say it goes milky as well, which indicates that carbon dioxide gas is present. Again, pause the video if you need to add to your answers. Okay, in terms of combustion, you can have complete combustion where there is plenty of air, there's plenty of oxygen around. Think about this in terms of a Bunsen burner. Methane is the gas which is regularly used in Bunsens. It's the gas that you use in your home, in your stove, or if you've got a gas cooker. It's certainly the gas that we use here in the labs up in science. When there's plenty of oxygen around, you'll form carbon dioxide and water. So to balance this equation for methane plus oxygen makes carbon dioxide and water, on this side you've got 4 hydrogens, which means to get 4 hydrogens on this side you need 2 lots of water. That means now you've got 2 lots of oxygen here plus 2 here makes 4 oxygens. So you need to have 4 oxygens on this side, 2 lots of 2 makes 4. Make sure you've got out this equation, guys. You could be asked to write out similar equations such as this, but the key thing is whenever there's complete combustion, you make carbon dioxide and water vapour. Incomplete combustion, so if you close the vent to the Bunsen burner, you'll form soot, which is the yellow part of the flame. That's methane just reacting with one molecule of oxygen. There's less oxygen around. You form carbon, otherwise known as soot. That's what gives the flame its yellow colour, and water. Again, you've got 4 hydrogens here. So to end up with 4 hydrogens here, you need 2 lots of water. You've got 1 carbon over here, so you need 1 carbon over here. Otherwise, it's balanced because if you put a 2 here, there's 2 oxygens here, which means that there's 2 oxygens here. That is incomplete combustion where you've got little to no air around. The in-between situation is where you've got more oxygen than you've got here, but less than here. You'll form carbon monoxide, which is a toxic gas. So here you still form water. To balance it, again, you need 4 hydrogens, 4 hydrogens. On this side there, you've got 1 oxygen plus 2 oxygens, which makes 3. So you need 1.5 oxygens, or you could double everything here. You could have 2 methanes, 3 oxygens, 2 carbon monoxides and 4 waters. But this is the most straightforward way to balance this, 1.5 molecules of oxygen. Can you make sure that you've got these in your notes? If you need to pause the video to do so, to get these down in your notes, please do so now. Okay, next little task, guys. I want you to imagine you're a carbon atom in the fuel. That's what will go here. There are various different spaces for you to write these different sentences in here. I'll give you a hint. This is loads of oxygen. This is little oxygen. Give it a go, guys, writing through the answers. So if you're a carbon atom in a fuel, guys, if there's plenty of air, it will undergo complete combustion. If there's limited air, it will undergo incomplete combustion. If there's little to no air, it'll undergo incomplete combustion. So the level of oxygen here is dropping at each stage. If it's complete combustion, you'll form carbon dioxide. If it's incomplete combustion, you'll form carbon monoxide. Mon means one. Think monobrow. Monobrow, that means you've got one eyebrow you need to pluck in between your nose. And if you've got carbon or soot, that's from little to no air. It's incomplete combustion. Think of a Bunsen. This is when the vent is open. This is when the vent is closed. If you need to pause the video to get this down into your notes, please do. Okay, carbon monoxide then. Carbon monoxide occurs from incomplete combustion. Carbon monoxide is an odourless, tasteless gas. If the room you're sitting in now was full of carbon monoxide, you wouldn't know about it. You may have heard in the news, and this case was only resolved recently, that I think it was back in 2007, there was a family that went on holiday to Corfu. And very, very sadly, Bobby and Christy Shepherd, who at the time were aged 6 and 7, they're from Wakefield in Yorkshire, died when they were on a holiday on a Greek island, Corfu. They were staying in a flat with their parents, and unfortunately the landlord of the flat hadn't gotten the boiler serviced and there was no carbon monoxide alarm. If you have a boiler in your home, it's absolutely critical, this is a boiler that runs on methane gas, that you have a carbon monoxide detector in close proximity to the boiler and you make sure that the boiler is serviced. The boiler here wasn't serviced, so as a result, these two children died because they went to sleep one night and didn't wake up in the following morning. And since then, there's new legislation that's been brought in as a result of this to make sure that landlords have their boilers serviced whenever you're going on holiday on a regular basis, to make sure that complete combustion occurs, that enough oxygen can get to the fuel to ensure that there is complete combustion. Okay, if we've got time, guys, here's some questions for the textbook. There's plenty of questions here. The cover teacher has the answer to these. You can pause the video and write these out nice and neatly, or at least the answers to these questions, in your exercise book. There are more on the next slide if needs be. Here's an additional question, which is a higher question. If you're feeling like you're really up for an extension challenge, give this a go. As I say, the cover teacher has the answers to these. If you haven't gotten around to this, never mind. Okay, as a plenary activity, guys, these are the key points of combustion here on the screen. Rate yourself red, amber and green for these learning objectives, if you like, and I will hopefully see you next time. Otherwise, we will look at cracking next lesson. If there are any problems, please message me through Teams and I'd be delighted to help you. Thank you for your attention.